gravitational
Thank you very much.
and mesoscopic quantum systems. Thanks, Francesco.
Thank you. I'm sorry. Just a moment. Can you see my screen?
Yes.
Okay. Well, before I start, I would like to thank the organizer for giving me the opportunity to be part of this very exciting meeting on the production and the detection of ultra-high frequency gravitational waves. And as you see from the title, my talk is about gravitational waves in a mesoscopic quantum system with a special focus on particle creation in graphene. Well, this is a brief introduction. As you know, mesoscopic system represent a bridge between the quantum physics and the classical physics. We are about at the nanoscale. So mesoscopic system allows several quantum effects to appear also at the nanoscale or perhaps above. We studied the interaction between gravitational waves and a microscopic system because we are interested in the possibility to investigate the relationship between, in general, gravity and the quantum mechanics. Also, interaction between such system and gravitational waves represent a possible arena in which we can search for novel effects might be related to new physics. Also, take into account the possibility of experimental detectability. Finally, at a mesoscopic scale, gravitational wave can be described as time-dependent perturbation only, because in the UHF regime, the gravitational wave or the considered wave, the gravitational wave is very large when compared to the typical scale of the interacting quantum system. This is a simple classification of the interaction between mesoscopic quantum system and gravitational wave, taking into account the induced effects. We have a parametric amplification effect. I see, for example, the case of Bose-Einstein condensate, or also interference or resonance effect, as in quantum interference in discrete or magnets in ferromagnetics, or also transport effect about, we will consider just this case as a specific case for the graphene. And finally, there are also vacuum fluctuation and vacuum energy effects, as in the case of Casimir effect, static or dynamical, for example, in the nanocavities. There are some examples. We have Bose-Einstein condensate, as we have seen 2 days ago, or superconductor, or ferromagnetic sample with magnon resonance, and finally nanocavities in which we have particle creation in a confined quantum field. Well, I will focus on the interaction between gravitational wave and the sheet of a monolayer graphene. We point out that this analysis is basically theoretical, so that the result do not take into account several complications due to temperature, impurities, phonoscattering, and so on. Also, no specific assumption about the form or the frequency of the gravitational wave have been made, so that I think that the present study can be applied also various forms of gravitational waves and periodic, impulsive, and other waveforms, for example. This is an outline of the talk. We start with a glance to some electronic properties of graphene. We then write down the DIRAC-WEYL Lagrangian. From the Lagrangian, we derive the equation of motion and the free Hamiltonian for the graphene. Then we introduce the gravitational interaction, and then we got the gravitational Hamiltonian in the graphene. We then move to evaluate the part creation, electron hole part creation in the field of weak gravitational waves. Just if time allow, there is a slide about stochastic gravitational wave background. And if time allows again, there is a final part concerning modulation in the direct current conductivity in graphene induced by weak gravitational waves. And then we finish with some conclusions and future proposals. Okay, as you know, graphene is an allotrope of carbon. It is basically a two-dimensional honeycomb lattice. And as you can see, this is, sorry. Use the pointer. Okay. As you can see, the structure is based on a unit cell containing two atoms, so that because we have to do with a two-side basis, the electronic wave function is represented by two-component spinor, which has sublattice pseudospin 1/2. And one of the most interesting aspects of graphene is that if we consider the low energy excitation, which usually call electrons and holes, then such excitation behaves as massless fermions. So that the governing equation is basically a two-dimensional Dirac equation in the framework of a massless fermionic field theory. The particularity is that the limit velocity is not the speed of light, but is the Fermi velocity, which is about 1 million meters per second. And we will consider the low energy limit. In such a limit, the dispersion for the energy is typically linear, so that the energy band in graphene have a conical shape. They're called as Dirac cones, like this. Okay, and you can see here the conduction band and the valence band. Conduction and valence band meet at the tip of the cones at the corner of the brilliance zone at 2 points that are the Dirac points, and K and the K prime that are not equivalent. We are here in the reciprocal lattice in the momentum space object. Now, if the interwelling mixing is negligible, that is as in the case of an external potential, which is smooth on the lattice scale, we may consider simply one Dirac cone, so that we have not to take into account such a mixing. And this is surely the case of a weak gravitational wave, when the gravitational wavelength is very large with respect to the typical scale of the graphene. Okay. Well, the starting point is the two-dimensional Lagrangian for a two-component spinor, and for the wave function of the electron in graphene. We consider a monolayer graphene sheet, okay, and we suppose we are in the XY plane here, so that the Lagrangian is like this, and the sigma 0 and sigma I are the Pauling matrices, and the psi is the two-component spinor for the electron inside the graphene. Well, if we are on lack of external perturbation, we can obtain from the previous Lagrangian the equation of motion, which are like this, or in matrix form. Okay, you can see now the two components of the spinor. And now let's look for solution having the plane waveform in the following form. And then it is a simple task to solve the eigenvalue problem. And we get the Hamiltonian, the free Hamiltonian for the system, as well as the eigenstate and the eigenvalues. H plus is the wave function for the electrons in the conduction band here. And C minus represent the waveform for the holes in the valence band. Yeah. This is the Dirac point. The energies are conventionally taken as positive above the Dirac point and negative below, so that the Fermi energy is taken to be equal 0 at the point in which the two Dirac coins touch each other. The momentum of the electron is in the plane px, py, and phi is the angle giving us the direction propagation of the electronic wave. We are in the ballistic regime, in which we suppose that diffusion effects or scattering effect is negligible. This angle appear in the free Hamiltonian here. Well, a word about helicity, because since low energy excitation in graphene behave as massless particles, they have a well-defined helicity. This is the helicity operator, and we can see that the Hamiltonian eigenstate are also eigenstate of the helicity operator, so that the Hamiltonian and the helicity operator commute each other. Okay, so in other words, the helicity is a conserved quantity for graphene. Now, what is the motivation for considering graphene in combination with the gravitational wave? But there are at least two reasons for this. The first one is that the peculiar structure of graphene represents an excellent example of a confined two-dimensional quantum system interacting with a gravitational perturbation. And also, the physics of graphene is a quite a promising arena where the interaction between, generally speaking, gravitational waves, not other types of gravitational fields, can be explored in combination with a spinor field. Now, let's introduce the gravitational interaction. And this is rather standard. We have a weak gravitational plane wave, which is propagating along the z direction, so that it is orthogonal to the plane of the graphene. And this is in the TT gauge, the resulting spaceline element. We see here the H plus and the H cross polarization states of the wave. Notice that since we take Z equals 0 at the graphene location, the gravitational perturbation depends only on time. Okay. We make no specific assumption about the form of the gravitational perturbation, so that we take a general function f for describing the gravitational waveform, where H plus and H cross represent the wave amplitude of the two polarization states. We also introduce, for convenience, the helicity states of the gravitational wave as a linear combination of the two polarization states of the wave, like this. And now we use the linearized theory to get the gravitational interaction Lagrangian. We take -1/2 of the perturbation, the gravitational wave, times the zero order, basically the flat space-time stress energy tensor of the matter field, namely the graphene. And from the standard technique, we get the relevant components like this. And we now put things together so that we get the correction, the gravitational correction to the flat Lagrangian, like this. We form the total Lagrangian, and then we obtain the equation of motion in presence of a gravitational wave. We see that in the quantity in the square brackets, the function psi can be considered as the zero order solution at the present order of approximation. Well, from the above equation of motion, we can obtain the gravitational Hamiltonian, which is like this. Okay, and here we see the Fermi velocity, the momentum of the wave, and the direction of the electronic wave, and E plus and E minus represent the polarization of the gravitational wave. There is an important point here that if we now evaluate the commutator between the full Hamiltonian, not the free, but the free part plus the gravitational contribution and the helicity operator, we see that in general, we have not conserved the helicity in presence of a gravitational wave. Now, consider the particular case in which the graphene is intrinsic graphene, so that we have the valence band, which is completely filled, and the conduction band is totally empty. And in this case, the wave function for the valence band is given by psi minus, and we take for definiteness a monochromatic gravitational wave like this. Omega g is now the frequency of the gravitational wave. If you observe the interaction during a given time interval, then the transition amplitude for the creation of the electron-hole pair is given by this relation, psi minus and psi plus, are the two wave functions for the valence and the conduction band. And this is the gravitational Hamiltonian. Now, use the psi plus and psi minus expressions together with the gravitational Hamiltonian, and we get the following amplitude for the transition. This quantity, depending on the integration time, can be considered as can be converted in a Dirac function in the large integration time. And if we square the previous result, we get the transition probability, which is like this. And you can see that basically it is a resonance effect, because the energy of the particle, electron, and the holes in the graphene is obtained by the energy, so to say, of the graviton. Okay. In this expression, the angle chi here is a measure of the polarization state of the wave. And now we can see that the commutator between the Hamiltonian and the operator, the helicity operator, behaves also in the similar way at the transition probability, so that where we have conservation of helicity, namely this quantity is zero, we have zero also the transition probability. So in other words, the electron hole pair creation is forbidden along those direction space in the XY plane of the graphene, where the interaction with the gravitational wave guarantees helicity conservation. Okay, and finally, we have to evaluate the number density of the electron hole pairs. And we integrate in polar coordinates, and we get, in this case, we are using a monochromatic gravitational wave, we get the following result. The interesting thing is that the number of created electron hole pairs grows with the self-power of the frequency of the gravitational wave. Unfortunately, this is a second order effect. So the result is, the expected result is very, very small. It is for depressed for the value from the value of the Fermi velocity. And we will briefly discuss in a minute below. I skip this because I'm a bit late. Skip this slide, and I want to show you what we can say about the current density in graphene. This is interesting because when we produce a number of electron pairs in the graphene, we also expect a change in the conduction of the graphene itself. This is the current density in graphene. The integration is over the Brillouin zone. This is the gradient of the Hamiltonian in the momentum space. And if you put the free Hamiltonian in this equation and apply the result, the formula to the case of a conduction band, for example, where the Fermi energy is in the conduction band, we get obviously the result is 0 because there is no driving field moving the current. But if you introduce an electric field, then we have the possibility to solve the equation considering the perturbation due to the electric field and with a correction to the waveform of the electron. And this can be evaluated in the semi-classical approximation like this result. And now we can evaluate.
There's 4 minutes left.
Thank you very much. We evaluate the DC current in this case, and we get the corresponding DC conductivity, which is the quantity in square brackets. This quantity in color is the density of state, which we can control by means of some electronics outside the graphene. And the interesting thing is that, let me go direct here. If we add a gravitational wave, then we have a photon perturbation. And in the linear regime, the total perturbation, the sum of the perturbation due to the electric field and to the gravitational field, so that the Hamiltonian is like this. This is the gravitational correction. And now the relevant correction to the DC current density has the following form. And we see that the correction is now first order in the gravitational wave amplitude. And also, due to the combination, the helicity amplitude of the gravitational wave, we have also a polarimetric effects, so that it is selected only one of the two gravitational wave polarization. This is the current density on lack of gravitational wave. So here are the conclusions. Gravitational wave can indeed induce a pi creation, electron hole pi creation in intrinsic graphene. It is a cumulative effect. Ideally, it increases with the integration time, and the number density of created pair goes with the gravitational frequency. Potentially, this is interesting for ultra-high frequency gravitational wave detection, but unfortunately, it is a very, very small second-order effect in the gravitational wave. From this point of view, so, it could be of some interest to seek for materials where the Fermi velocity is very, very small, because this could contribute to rising the number of created particles. On the other hand, the gravitational wave can also induce modulation in the conductivity. Now the modulation has the same frequency as the frequency of the incoming gravitational waves. It is not, in principle, a cumulative effect, but it is a first order effect in the gravitational state. And also it exhibits polarimetric properties. So what one can do in the future, we need a deeper investigation of graphene transport in presence of gravitational wave. We need to study in detail the response to a stochastic background of gravitational wave we are interested to extend the previous analysis to other geometries that take into account also possible two-dimensional graphene realization. I think, for example, bilayer graphene. And we search also for other materials with a very small value of the Fermi velocity. And finally, it is important to evaluate in detail the expected order magnitude of the predicted effect for possible experimental detection, and search for possible experimental setups in collaboration with experimentalists. And this is all. Thank you very much for the attention.
Okay, thank you very much. Is there any questions? So I have more of a comment, Francesco. When I did my work with the BC that has some elements in common with what you do, when you just look at, you would take the BC and put it in the ground state. And if you look at the phonon creation there by a gravitational wave, it's absolutely negligible. I guess it's also of a lower order. But what we did is that if you put like phonons in a quantum state, then that's when it has the enhancement. So maybe you could try to, I mean, I know you have the other effect, which is first order, and that looks wonderful. I was actually thinking, oh, maybe there's another first order effect on my case. And it's good to look at these two things because, you know, yours gives me ideas, but maybe mine could give you some ideas. And what we did is that we don't look at how the gravitational wave creates phonons, but we see how the gravitational wave modifies the state of already existing
phonon. Okay, yes. Yes, in that respect, it is very similar to what I said about the DC conductivity. It is a first order effect because the gravitational wave acts upon a pre-existing background of phonons or so on, yes. And basically, it is the only way I see as a realistic way to construct, realize a detector for such a thin gravitational perturbation, yes.
Yes, okay, yeah, no, that's super interesting. I was very happy to follow so well as I could.
Thank you very much.
There is a question by Sijun. I don't know if I pronounced your name correctly. Excuse me if I didn't, please. Go ahead.
Do you hear me? Yeah.
Yes.
Yeah, very, very nice talk. Thank you, the organizer. I just have one question. So this detector, it sounds, including the solid state and graphene detector, sounds very similar to those dark matter, light dark matter detector people has been talking about before. You know, I don't know whether, because it seems like they have made some progress on especially on the solid state on different crystal detectors and the graphene superconductor. So I don't know whether one detector can do both, or have you guys talking to that community?
This is an ongoing research on various materials. So the basic idea is to search for possible nanomaterials which can be used to detect gravitational wave at ultra high frequency regime. And so, no, I have not considered those issues. Oh.
Yeah, because I feel like maybe one detector can do both. And yeah, I don't know. It's just there are lots of study on those. Well,
it might be, I don't know.
The group in Berkeley.
It is possible. It is possible.
Yeah, thank you.
Thank you.
Is there any other question?
A very quick one,
Well,
if I can. Just wanted to know, I mean, is this project something active at the moment? I mean, are you planning to work on it?
It is simply a theoretical research. The numbers, the sensitivity is very, very small indeed, because concerning particle creation in graphene, the amplitude of the wave, it is at the second order, we get a ridiculous number of particles created. And so we need to improve the technique. I think, for example, to a large scale integration as in the microcircuits, but I don't know what is the state of the art with graphene. It is a newborn as such. So there is no active project on this.
Thank you.
Thank you.
Okay, thank you very much. So we'll go to our last talk of this session. So that's Camilo Garcia Celi with cosmological detectors, please.
Hello.